What I really liked just now was this remark by Annemarie about that we all need our noses in the same direction. And I think about 2 years ago or something, Johan and Mark approached me with a similar question. They said, we have this very interesting idea, but we need to actually show what the impact is, or first calculate what the impact is, and then show that message, convey that message to people who have to do it, the local policymakers, the grid operations, the grid operators, the energy cooperatives, and so on. So we need to calculate the impact and then convey that message. And that's what we went to work on. So first, shortly about me, what I do. I'm a PhD student at the TU Eindhoven, and there we make all these kinds of energy transition models in a multidisciplinary research project. So we really take the regulatory perspective, the social perspective, and the more technical perspective. And within our small little company ZenMo, we try to take all this information and bring it to the public faster, because we see that we have all these fantastic models, but we need to convey the message faster. So that's what we did with Deel de Zon as well. So what was our exact goal? Well, the first goal was to explore the potential of this system, as I just said, the entire concept. So the shared electric cars, the large rooftop PV, and the bidirectional and smart charging in the actual system where it would be placed, so the actual local context. And then we would show what the impact would on, in this case, specifically grid congestion. I think grid congestion is really one of the bigger issues of the energy transition right now, and a lot of developments are being hindered by it. So can we alleviate that grid congestion with this vehicle-to-grid concept? Well, the setup that we chose is we made a digital twin of the e-neighborhood, so focused on where the actual Deel de Zon system would be. We chose that neighborhood and we made a digital representation of it. So we modeled all the households connected to the same transformer as the Deel de Zon thing, and we modeled all the charge points and the PV systems. And in this, I think it's very important, especially looking at this grid congestion problem, to make things like an agent-based behavior model, so that you really know when will the people in these households use up electricity or have mobility demand. Also, the mobility demand, for example, of shared vehicles is quite different from the mobility demand of private-owned vehicles. So these are all things that need to be worked out and researched, put into models to see what the impact is and how that could work out. So what is the structure of this map? What did we make? What did we choose it on? So we based it on the GIS maps with public Bach data. This data was mainly used. The second thing I think I would like to stress is when researching such a thing as V2G, you really need a system perspective. So you cannot just investigate the impact of grids of mobility. You would also need to take into account electric cooking, electric heating, and other coinciding developments we have in the energy transition. So therefore we looked at the Bach data to see what kind of houses there were, to see what heating profiles they would have. We had open source location data, open source grid data from Inexis, OVIN travel behavior. So based on all these travel studies, we represented the behavior which we currently see in traveling patterns, and the Buur auto travel trips. So to kind of differentiate between traveling trips from shared vehicles and from privately owned vehicles. And there are a lot of user-defined characteristics, because as said, we want people to understand this system and to understand the implications to convey the message. And therefore there's a lot of uncertainties, how fast the transition would go, what kind of the amount of electric cooking, electric vehicles, PV in this system would be. So we opted for a lot of user-defined characteristics so that the user themselves can work with this model, play with this model, and try out different scenarios. Well, this is a brief clip in which I will show the most important aspects of the model. I hope it's playing right now, but we'll see in a second. So as said, there's a lot of user input defined in this model. You could select a couple of neighborhoods. Of course, the location matters a lot. And you could investigate different months in the year to evaluate what would be the differences in summer and in winter And then second, I think an important characteristic is that you can select, of course, the charging strategy, but we made the difference between the setup of the Deel-de-Zon system itself and the rest of the neighborhood. Let me see, it was not playing. Let me see if I can speed it up a little. So yeah, the Deel-de-Zon system is in the left top, where you can figure out, okay, in such a setting, how many shared EVs do we need? How many smart charging or bidirectional chargers do we need for all these EVs? And in the right, we see all the settings for the neighborhood itself. Then when you have done all the settings, okay, I think there's something wrong with the video. So unfortunately, you cannot see the model play out in real life. That's a shame, but if you want it, you can see it later, or there's also a short clip on it on YouTube, so we can refer to that later on. Fortunately, I did copy some of the most prominent results again in the slides. So what we did here is first show the worst case scenario. The worst case scenario is that a lot of people in this neighborhood will actually buy electric vehicles and do nothing with their charging. So do the UCS, it's called uncontrolled charging strategy. Well, I think we all know that that would result into problems. So this is not a big surprise here. But how can we alleviate this problem? What are the biggest things we need to do? So now again, we have the next situation in which we try to alleviate the problem with the Deel-de-Zon concept. And I think it works quite a bit. So the blue line is the worst case scenario, and the black line is the Deel-de-Zon concept. So actually now in this case, the V2G cars owned by Deel-de-Zon, charged by their PV system, they help to reduce grid stress when there is a lot of grid congestion. But of course, as you can also imagine, only so much Deel-de-Zon cars can alleviate ordinary cars. So there's kind of a balance in there. If there's a lot of EVs, you would also need a lot of V2G charging Deel-de-Zon cars. And in this case, I think we had about 16 Deel-de-Zon cars in the system, which was not enough if you have a location with a lot of ordinary, uncontrolled charging cars. So we still have this problem of grid congestion. In the next slide, we see what happens. Now, actually, there's two important things in this slide. So we again use the Deel-de-Zon system with, but in this case, the other cars, the privately owned cars which are still there, will do smart charging. So this is, I think, the biggest impact for grid congestion, at least in the concept of demand-side congestion. But on the other hand, we also see now in summer, there's a lot of PV generation. And this PV generation in the smart charging concept is not really, or the cars cannot really alleviate all or handle all that PV generation. And in that case, I think V2G charging cars work really well to handle more of the PV generated electricity. So the conclusions, I think we did well. We can easily also, I just showed you the results for one neighborhood. We can easily expand this to multiple neighborhoods. In the end, we made, I think, 7. And they all show slightly different results. So we can easily model that and show that. It largely depends, the impact, by the way, then largely depends on actually how many charge points there would be allocated to one standard transformer, which of course makes sense. And I think that we can say V2G really proved successful in reducing grid congestion from other charging EVs and to reduce curtailment from PV. But that's of course in a balance with how many other charging cars affect. So as I said, the rest of the system really makes a big difference in how well your V2G system in how well you can actually alleviate these grid congestion issues. So generally speaking, V2G works a lot, but maybe there's so many other cars which you cannot control that you still do not have enough capacity. So therefore, I would say smart charging remains top priority. And indeed, V2G is really useful in the case you would need additional batteries anyway to store or to use your PV generation more effectively. Of course, V2G really makes sense there and helps to store that excess battery in the summer. And one last remark I would like to make. Another thing which really needs some attention in showing the impact of V2G is actually which tariff structure are you going to handle? So on what prices are you going to use your V2G algorithms? Will there be any grid tariffs or the bandbreedte tariffs or any of these other things? There's a lot more research and you can go way more in depth to really evaluate these results in more detail. So we're also working on that. Unfortunately, the presentation here is a bit too short to dive into that a lot deeper, but if any one of you are interested in it, yeah, I would like to talk to you about it. And lastly, I think, so this model, unfortunately, you couldn't see the demo right now, but it's really aimed at policymakers, people from the DSO, and people from energy cooperatives. And it's not just to show you the perfect results, how well does it work, how well doesn't it work. It's to explore what the pros and cons of such a system are together so that you can understand when it works, when it doesn't, what are the top things to do, and what works less good. Thank you.
Thank you, Naud Loomans.